Thank you for this opportunity to talk. The title must be, you guys must be wondering, can you be more vague? So that's what I'm going to aim at. I'm going to try to list a few examples which has polynomials involved somehow. I mean, how can it not? And then try to sort of look for a thread of commonality in those few examples and talk about something called homological. So let's look at some examples of moduli spaces, which are spaces whose points represent some algebraic geometric object of some kind. So some examples would be, so capital K, there is a field, you can think of complex numbers, and if you take degree n monic square-free polynomial, the space of degree n monic square-free polynomial. So that's a moduli space. That's a space of polynomials with some constraint being square-free. There is a sort of, in a sense, it can be called a higher genus version, where you can take C to be a compact Riemann surface of genus G, and you can take a line bundle L on it. If L satisfies certain conditions, you can then ask for all, I wanted the laser. So you can ask for all those global sections of L, which have, at any point, its multiplicity has to be strictly less than 2. So it's kind of like mimicking the square-free notion, if you think about it. Yet another example is R+1 tuples of degree n polynomials having no common zeros. Let's take those polynomials to be like homogeneous in some number of variables. So in effect, they end up being, depicting the moduli space of morphisms from one projective space to another, which, you know, they need not admit morphisms unless like G is less than or equal to R. But keeping that aside, all these spaces of polynomials with some constraints, they all represent some sort of a moduli space. One and many more. So one thing to note about them is that they come in sequences. This is going to be super important for us. In the first case, there's degree n. So n is sort of, you can take various n for various moduli spaces. In the second case, you can take like, once you have a line bundle, you can take like more and more tensor powers of it, L squared, L cubed, and so on. In the next case, yeah, you can take n, or you can take this R, you can take this D, but I will be mostly focusing on the n, just to be clear. So they come in sequences. A non-example, I mean, it's not a non-example of moduli space. They're very much an example of moduli space, but for us, it will be a non-example for our purposes, is this wonderful, interesting moduli space MG of smooth, projective, I did not write the words projective, actually, it should have been there. So our compact Riemann surface of genus G. So genus 0, genus 1, that's genus 2. The points of MG look like each point of MG, so each point of M2 represent this genus 2 curve with a complex structure. There are some things that needs to be done about genus 0, which I'm not going to talk about at all. So it's a non-example, so let's not dwell on that. So we wouldn't be considering this space in particular. Okay, so all these moduli space come in sequences. And what do we do about that? So interesting question often is, well, it was probably started by Quillen, if I'm not mistaken, homological stability. And it has, so I'm going to talk a bit about what homological stability is and how it affects something called arithmetic statistics, and sort of say how, what sort of information this gives us for the examples we talked about initially. So a sequence of spaces, let's suppress the word schemes for now, Xn are arising, suppose, naturally in some fashion. We say that Xn satisfy homological stability if we can construct natural, quote unquote, natural maps from the ith homology of Xn to the ith homology of the next space in the sequence. So in a sense, these natural maps have to be isomorphism. So in a sense, what homological stability wants is that Xn satisfies homological stability if the low degree homology of these sequences don't really matter which stage of the sequence you're at. So that's homological stability. And what about arithmetic statistics? If you have, say, schemes over Z, some algebra geometric thing over Z. So there is this, I'm writing the word, but I'm not going to get into at all what this is. But if you have, so if X is scheme over Z, so suppose X is defined by some polynomial with integer coefficients, you can extend scalars by like taking the complex points, complex solutions of that polynomial, or you can take like mod p to the n solutions of that and ask how many there are. This amazing package of Weyl conjectures relates the cohomology of the complex points, is what it's called, with the number of FQ, the finite field number of points. So when, in the case, if these xn's are schemes over Z, for example, then the fact that homology, if xn's satisfy homological stability, then much can be said about the asymptotics of the FQ points of these xn. And so often one route to understanding what this kind of limit looks like is to somehow try to show that the homology or the cohomology of this space stabilizes. And some of you might be wondering, what sort of, am I a singular cohomology analysis? Do I need a thought, stuff like that? I'm going to completely ignore that for the purpose of this talk. Right, so I should mention the names that these things are attributed to because they are super important. Weyl conjecture, I should have mentioned Dwork's name. I'm sorry about that. There's Grothendieck, there's Deligne. For homological stability to arithmetic statistics, there have been a lot of wonderful work done about it. Some of them are, in the case of, for coherent Lenstra heuristics, when the moduli space are what are called Hermit schemes, Ellenberg, Venkatesh, Westerland's work is there. And then there is Farb, Wolfson, Wood, and many others. Okay, any questions so far? Any notation I should clarify? Okay. So I said that I want to talk about the homological stability of some of the spaces that I initially mentioned in the first slide by extracting some common thread. And that common thread is precisely what's called configuration spaces. So let me define what that is. So the unordered configuration, so X is a space. I'm just loosely talking about space without defining schemes over here. So unordered configuration space, you take the moduli space of n subsets of X. So that is contained in naturally inside this is the symmetric n-fold symmetric power of X. So you take like nth Cartesian product and go modulo the symmetric group action, which, yes, if you're wondering, it's not free, of course. And that sort of can bring technical issues, but again, I'm not going to get into that. So that's unordered configuration space for us. And there is a slight variation of that, which we would not need for the talk. I just mentioned it because if the experts are wondering, okay, yeah. So turns out the space, configuration space, the nth configuration space of X, unordered nth configuration space of X, satisfies homological stability. And much work has been done about that. So initially, in the case of X, I think is it just R2 or maybe for any Rn? I'm not sure, maybe somebody can correct me. It was done by Arnold. For more general manifolds, like for even closed manifolds, it was Tom Church. For smooth projective varieties in general, Totaro. And I just want to say that, like, how does one, I mean, of course, there is no one single strategy to attack any homological stability question, but one popular way, in a sense, of trying to understand homological stability is to try to construct a map, say, from conv nx to like n+1, so that it induces map on homology, and maybe you can try to prove it's an isomorphism. So when X is, suppose you take X to be just the complex plane. In that case, getting a map from conf nc to conf n plus 1c is, there's a nice map which sort of what it does is, so suppose you have n points on the complex plane. It's clearly inside some, like you can draw a disk which contains all those endpoints. And then you add a point outside that disk. That kind of idea is popularly called adding a point at infinity. And you can sort of, you can do it in a continuous, nice fashion to get a map from like n points configuration to n plus 1 points configuration. And that indeed ends up giving you stability of homology for even open manifolds. Because for open manifolds, you can sort of still kind of mimic this notion.
So the conf nx is distinct points and distinct points? And
distinct points, yes. So like n subsets of, yeah. So from the symmetric powers, you take out the diagonal, so to speak.
Right, exactly.
And as I said before, so when there is homological stability, there is always some, like, you should smell some arithmetic statistics going on. So in this case, when x equals c, not only the homology stabilizes, there's only 0 on the first homology, which are non-zero, and they end up giving like the FQ points of conf and C. So the square-free the number of square-free polynomials over FQ is that. Okay. I just want to mention that even though we don't need it for our purposes right now, there is another thing which also goes by just configuration space, which is the ordered version, which is x to the n minus all the diagonals. Okay, so so I gave some examples, I gave some thread of commonality. I want to go back and just say why I'm making such a fuss about configuration spaces. Well, in the first example, it's super obvious, it is a configuration space. In the second example, well, notice that in all these examples, if you kind of remove this constraint that your polynomial or that your section has, like having a strict multiplicity of less than 2 or having no common zeros, the complement of these constraints are like allowing points to collide. So like a section, suppose, has 2 distinct zeros, but those points can collide and then end up giving multiplicity 2, right? So having or wanting distinct points and the complement depicting some sort of collision of points, that is what kind of brings the configuration space somehow or the other into the picture. I should make a statement here. By no way does it mean that I'm saying the stable homology of these spaces is the same as the stable homology of configuration spaces. That's not true. But somehow configuration spaces come into the picture. Okay, I will be going to quickly a sample theorem, which has a lot of words in it, but I would request you to just listen to my words. This space, this fancy L12NG, is essentially the moduli space of maps from a fixed genus Riemann surface to a weighted projective space P46. It's so consider, instead of A, replace it by, say, C, and take capital N to be 1. So that's C2 minus the origin, and you go modulo scalars by like a weighted scalar action. So that's a weighted projective space. I want to specifically take P46. And L12NG is the moduli space of those morphisms of a fixed degree from a genus G curve to that weighted projective stat. And now I did not write I'm not writing the homological stability result because that's like a huge complicated version. But let's look at the FQ points that it results in, because there is a dominating term, the highest power of Q. And what ends up happening is these coefficients, they, up to a certain stage, they end up being independent of N. And I want to just make a observation. Sorry, where am I? Yeah. So I want to make a quick observation. If G is 0, like if you're taking P1, the Riemann sphere, this count is just Q to the 10n minus Q to the 10n minus 1. Like the rest of the AIs vanish, which is, if you think back, it looks very close to what we had for configuration spaces, Q to the n minus Q to the n minus 1. So what next? Well, there are several questions that one can ask along these lines, configuration space-ish lines. But some of them would be like, what kind of target varieties we can take that might give this kind of like, that might somehow split the problem into understand configuration spaces, understand the geometry of some bigger spaces, and then sort of punch them together. So in the case of X, when X is a toric variety, if you take, say, maps from a smooth projective curve to toric variety of a fixed degree, you have to define some notion of a degree. Yes, we have a positive answer. Much can be done about it. There is a stability result, and ignore the word partial monoids, but like configuration spaces of some sort come into the picture. When X is a Grassmannian, well, maybe is like quite possibly this kind of regime works, but a lot needs to be done there, and it's not really well done. When X is a hypersurface, I write very unlikely here, but read that as like next year, at least for me, it's next year possible. Because general hypersurface need not even receive non-constant maps from P1, forget any other higher genus thing. So just knowing about configuration is not going to help much. So the next question you can ask is really, how far can you push this? Like, what X can you have so that that kind of configuration regime works? And it's suspected in a very loose way, if X is cellular, then knowing about configuration spaces and implementing them can answer quite a bit about point counts. So if I do not succeed in reaching across to the general audience, I want to end on a slightly humorous note. Thank you.